Although we can only measure differences in energy and entropy, a quick glance at any thermodynamic table will show that we routinely assign a value of the entropy to standard states. How is it that we can calculate the absolute entropy of a given state? As we did with the energy, we're going to define a reference state for the entropy. Let's think about what the most logical reference state would be. Since we know from the second law that entropy is always increasing, there must be a state with the minimum possible entropy. If we assign this minimum entropy state to have zero entropy, that will be our reference state. The state with the lowest entropy will be the one with the least number of microstates. So if a system has every particle in the ground state, then there will be only one microstate available to the system. Remember that temperature affects the number of microstates that are available to a system. So at lower temperatures, the system does not have enough energy, enough kinetic energy, to access microstates above the ground state. In fact, if we restrict the temperature to 0 Kelvin, absolute zero, then in fact the only state available to the particles will be the lowest possible state, or the ground state. And so at 0 Kelvin, the number of microstates available to the system is equal to 1. All particles are in the ground state, and so the Boltzmann entropy is equal to 0 because the natural log of 1 is equal to 0. And so we can define the system at 0 Kelvin, in which case all particles in the system will be frozen in place, and thus we have a perfect crystalline system as our zero of entropy. This statement is what is known as the third law of thermodynamics. Armed with the third law of thermodynamics and our second law definition for how to calculate the entropy, we should be able to calculate the absolute entropy of any system by simply integrating ds from 0 Kelvin to the temperature of interest. We know that the entropy changes with temperature according to the heat capacity divided by temperature. The left-hand side of this equation is easy to integrate. ds integrates to s, and then I evaluate from s at t, my temperature of interest, to s at 0 Kelvin, but s at 0 Kelvin is defined as 0. And so this gives me the absolute entropy at the temperature of interest. However, I run into a little bit of a difficulty when I try to integrate the right-hand side of this equation. Notice that if the temperature goes to 0, this integrand approaches infinity. And that's a problem, because then my integral will not converge. We can get around this problem by remembering what the heat capacity looks like as a function of temperature. And as we extrapolate to 0 Kelvin, remember that this extrapolation looks like C is proportional to the cube of the temperature. And so if at low temperatures we replace this cubic equation for the heat capacity, we can then integrate this at low temperatures and use our experimentally determined data at higher temperatures. So to do this, we're going to split our integral into two parts. one for low temperatures, where we go from 0 Kelvin to some low temperature, where the heat capacity is going to be proportional to the cube of the temperature. And then we're going to integrate using experimentally determined data from the low temperature limit, where we've done that extrapolation, to our temperature of interest using the heat capacity from the data that we have obtained. So, if we do this integral, we can see that S at the temperature of interest is equal to A, which is a constant, integrate from 0 Kelvin to T prime. T cubed over T is T squared dt plus our low temperature extrapolated temperature and the integral of C dt over T. Thus, the entropy at the temperature of interest is equal to A, which is this proportionality constant for this extrapolation and depends on the substance that I am looking at. The integral of T squared dt is 1/3 T cubed. When I evaluate that from T prime to 0, I simply get A over 3 T cubed, T prime cubed. And then I have to add from T prime to T the integral of the heat capacity for the measured values at the temperatures above T prime.